Hello guys, welcome back. So in the previous video we started with the principal component analysis. We saw what is the visualization of PCA. We saw that if suppose we have a data like this, we have to transform this vector space such that the new vector space is uncorrelated. So we get the data like this. We have some axis E1 and E2 and we get the data like this. So we proved what is the transformation. So we saw these steps and we saw that if we do this transformation, that is if we multiply the mean subtracted x, that is you subtract x from the mean, so you will get y, which is not, and you multiply it with the u transpose, where u is just the a matrix with its columns being the eigenvectors. So when you do this multiplication or this transformation, basically you will get a y, where y is this space. So y is this space, and in this y space the data is become uncorrelated. That is what we saw in the previous video. So now what we have to see is how do we identify what is E1 and what is E2. So now that we have done this, now what we have to do is, the next step that we have to do is we have to project all these vectors on the maximum variance axis. So this axis you can see has the maximum variance, this has the minimum variance. So we have to see which is that axis which is having the maximum variance. You project all other points on this maximum variance axis and you'll get something like this, and you just delete or remove the E2 axis. We no longer need the E2 axis, you have this only. And then when you will transform this back to the x1 x2 space, that is when we'll take an inverse transformation of this. So we'll see how we'll do that. So we get this, that was our what we say required thing. So we have compressed the data and still effectively compress the data, and things are done. So let us see how can we get this direction of maximum variance. So that is our objective now, to find the direction of maximum variance. So let E1 be the vector on which x is projected. So let there be some vector E1 on which all these samples are projected. So what is x? X is all the set of all these samples. So it is having every point over here. So this is 1x. So this can be, say, x1 is x2, x3, and so on. So now the projected vector is nothing but E1 transpose x. So this is the dot product equation. So basically when you will take the E1 transpose, so here this E1 is with respect to this x1 and x2, so it will also have some value, and that when you dot product with this, you will get the projected vector. So this particular thing, this will come over here. So this thing is the projected vector. So now also, because these are axes, so this is E1 and this is E2, so E1 is just saying you the direction, that it is in this particular direction. So in this vector space, E1 is telling that it is in this direction. So this direction is important, and E2 is saying this direction. So what we are interested is in the direction. We don't want the magnitude. So basically you always see in vectors, suppose there is a vector space, say, let me do it over here. So say suppose there is a vector space, some xy. So what we say is I is a unit vector along x. So it is a unit vector, this is important. So unit vector along x, and similarly say j is unit vector along y. Similarly, what we want to do over here is we want a unit vector along E1 and a unit vector along E2, or these unit vectors is what we want. So because of that, what we want to do is we want E1 transpose E1 to be equal to 1. So this is what is the unit vector. So when you take dot product of unit vector with itself, you get 1, right? So that is the same thing, the dot product of the, so if E1 is a unit vector, this is the dot product notation in linear algebra. So this will become to 1. So now variance of this projection. So what I am see, I don't know even now, I am finding even. So what I assumed is I have some even, I don't know what is this even now. I am projecting all the vectors on this even axis. So I'm going to get this particular output. This will going to be my projected vector. Now I want to maximize this variance because that was my whole objective. I want to know which is the axis. So here visually you can see that this is the axis which is having the maximum variance. This is having a very small variance, maximum variance. So this is what I want to find out numerically. So hence I am calculating the variance of the projection. So this is what I had. I projected this like this. So that is nothing but taking the dot product of every sample with even. That is what we do over here. And then we see the variance. So after this I'll get this, and we see the variance of this particular thing, and we want to maximize this variance. So the variance of this projection will be E1 transpose xn minus E1 transpose x bar the whole square. So we know that variance is given by 1 by n summation n is equal to 1 to n, so x minus x bar the whole square, where x bar is the mean of x, right? So this is what variance is given. So variance of x is given by this form. So the same thing is applied over here. So because E1 transpose is a constant with it is not any point over here, so that will come out and you will get just mean of these samples. So this is the formula of variance. Now what I did is I am opening this. So this was square, so I can write it this into this transpose. So please remember that in vectors x square is nothing but x into x transpose. So this thing I can write it this thing into this thing transpose. Next I have given transpose to both of them. So this so it is like I'm opening the transform, I'm making both transform like this, and then we know that AB transpose is equal to B transpose A transpose. So B comes in the front and A goes behind. So similarly when I open this, so this transpose will cut and x will get a transpose and they will shift. So it will be x1 transpose E1 minus this will also shift x transpose E1. That's next. What we'll do is we can take E1 transpose common from here and we can take E1 common from here, and what we are left is with this. So I can take E1 transpose out of the summation also because it is not depending, it is just the summation is just depending on x. So xn is all the samples over here. So this will be x1, this will be x2 and all the story. So from n is equal to 1 to n. So capital N are the number of samples. I did not mention that. So capital N is number of samples and xn is basically each sample. So here this will be x1, x2. So each sample is x, each sample from the set of samples. Yeah. Now so I took even out of the summation because it was not dependent on x, and you can see this much thing is nothing but the covariance of x. So the covariance of x will be given by this formula, which is what I had written over here. So the square is can be separated like this, and this becomes the covariance of x. So now that we know that the variance of this projected vector is nothing but you take the covariance of x, that is you take this covariance, the covariance of this, you pre-multiply it with E1 transpose and post-multiply it with E1. So whatever axis you are choosing, you pre-multiply E1 transpose, that is with that axis, and post-multiply with it the covariance matrix of x, and you will find the variance of this particular axis. Okay, so now our task is to maximize the variance with respect to E1. So I want to find out which is that E1, which is this E1 which will maximize my variance. So I want to find out which is this E1 axis. So is it this, or which is it? For n dimensional there can be many axes. So which is that E1 axis which will maximize my variance? That is what I have to find out. So but we have a small constraint. The constraint is that this E1 should be a unit vector. So that is what we have defined over here, that E1 is a unit vector. So we had some constraint on E1, so we used the Lagrange's multipliers method to optimize this particular thing. So we have also used this same method, you can see in the map method, I guess. No, sorry, not map method. We have used it in GMM for finding pi i's. So the same thing we are using over here, Lagrange's multiplier, because there was some constraint, so that there pi I also had some constraint. The addition should have been 1. That was the constraint on pi I. Similarly, the constraint over here is this. So for Lagrange's method, what we do is we make a function out of this this particular equation. So we are defining g of e, it is dependent on e, is equal to some 1 minus e transpose e1. So we want something like this. So it is like 0 is equal to 1 minus e1 transpose e, and this becomes my g of x, and that is what I place over here. Okay, so intuitively you can see that to maximize this, if I want to maximize this, oh, there's a minus sign over here. So if I want to maximize this, that means that I'll have to minimize this because there is a minus sign. So if this thing will become 0, then you just maximize this. So that is what we essentially do if this is 0. So if this condition is met, that if this is equal to 1, then this will become 0 and you will get the maximum. That is the basic idea of Lagrange's multipliers. So this is the formula of Lagrange's multiplier. You take in cost. This is what I want to maximize, my variance. I want to maximize my variance minus subject to this constraint. So this is the thing that I want to take care. And lambda 1 is nothing but the Lagrange multiplier that we apply over here. Now differentiate this with respect to E1 because I have to maximize my variance with respect to E1. Which E1, right? So I want E1. So because of that, I am differentiating. So when I differentiate, I get so this becomes 2 times covariance of x into E1. So we have seen those relations. How do this work? So it basically tells that if suppose you have some x transpose some a into x, where a is a matrix, x is some vector, right, and this is some y suppose, and I want to differentiate y with respect to x. So this is what I want to do. Then what I do is, so what the answer of this is 2 times a into x. So this is a relation that we have. This is matrix differentiation basically, vector and matrix differentiation basically. So that by this we get this, and similarly over here this 1 will go because 1 is a constant, minus. So uh, if suppose we have some y is equal to x transpose x, then dy by dx is nothing but 2 times x. That's it. So similarly this was x transpose x, so dy by dx will give you 2 times x. Now we are equating this to 0 because we want to maximize. So you equate the first derivative to 0, and you taking some algebra, so you're taking this term over here. So you can see this is the equation that we get. Now you can cancel 2 from both the sides, so you get this equation. Now you can see that this equation is in the form of ax is equal to lambda x, where this is a matrix A. So covariance, we know that covariance is a matrix, in fact a symmetric matrix. So we can what we say, compare it with A. E1 is a vector, so we can, so this was the form, the eigenvector form that you can see. So E1 is this x, so please don't get confused this x with this x. This was our data, this is the data sample, but here this is the standard eigenvector equation. So because of that I have compared this. So this is a vector which is equal to lambda times x, which lambda is a eigenvalue. So this is the standard eigenvector equation for any matrix A. So similarly you can see that this becomes an eigenvector equation for the matrix covariance of x. So from this we can conclude that E1 will be that vector, E1 will be that vector whose lambda, which is eigenvalue, oh I've written over here, so whose eigenvalue is the highest. So whichever, so what we'll do is, so eigenvalue of what, so eigenvalue of covariance matrix. So you take the covariance matrix of the data, you find out its eigenvectors and eigenvalue. So this particular direction is given by that eigenvector whose lambda, so if suppose there is lambda 1 corresponding to E1 and lambda 2 corresponding to E2, so if lambda 1 is greater than lambda 2, so then eigenvector corresponding to lambda 1 will be the direction of maximum variance. This is what we conclude from this particular derivation. Now our motive is to compress the data, right? So our motive is like, so what we did till now, we took, this was our data, we transformed it to this, we found out what is even. So now we find out what was E1. So we know that E1, this E1 is nothing but the eigenvector that is corresponding to the maximum eigenvalue of the covariance matrix of this data. So we figured out this. Now we want to remove others. So we want to remove E2 or any other which is over here. So now the main objective is to compress data. So now we want to compress this data, so we want to remove this particular axis, we want to remove those eigenvectors which have lambda small. So we saw that the covariance matrix of y, so the covariance matrix of this data is like this, of this form, lambda 1 lambda 2 lambda k. So you can see that lambda is nothing but, so lambda 1 is nothing but the variance along E1, because this is given by the covariance matrix of y. So the covariance of this, so lambda 1 is covariance of E1. Similarly lambda 2 is covariance of E2. So what can we do is, we can order this particular matrix such that lambda 1 is greater than lambda 2, greater than lambda 3, greater than lambda n. So we will get like this. So lambda 1 lambda 2 over here, because there are only 2, and you can see that lambda 1 is greater, so I have written, so lambda 1 is greater than lambda 2. This is the condition that I am taking. So I found out that correspondingly you can order the columns of U matrix. So U is nothing but, so this can be corresponding eigenvector of lambda 1 and x1 x2 of, so this is the eigenvector corresponding to lambda 2, and you can order this like this. So I have ordered the covariance matrix of Y like this. Similarly, I am ordering the corresponding columns of U. So the first column will be, so this is U. So the first column will be lambda 1's eigenvalue, eigenvector. Second will be lambda 2's eigenvector, and so on. Now you can see that all of these covariance matrix X will be K cross K, covariance matrix Y will be K cross K, and U will also be K cross K. So you can see over here. So if suppose there are n eigenvalues, there will be n columns of eigenvectors, and all of them will have n components. So all of these are K cross K. Now we want to reduce the dimension. I don't want to take E2 because I want to compress data. So don't take all the eigenvectors. Instead, just choose first d eigenvectors. So in this case, I will just choose the first eigenvector because it is giving me maximum. But then if there are many values of k, so if it is an n dimensional data, many dimensions, so 3 dimensional will be like this, but then other dimensions I cannot show, but we can have it practically. So for that you can just choose the first d dimensions of eigenvector, and this d should be less than k. You cannot choose more than the actual data's dimension, right? And now because you are choosing only the first d eigenvectors, so this will have only d rows because this is the transpose. So d rows cross k, we have not changed anything about the covariance of X, and the columns, there will be only d columns. So when you multiply this, you can see the covariance of Y will now be d cross d. So instead of taking all these eigenvalues, I have just now taken some d eigenvalues. So that is, instead of taking both these E1 and E2, I just took this. So I have just taken lambda 1 corresponding to it. I have taken E1. That's it. I have not taken E2. So when I transform, so I'll have to transform it such that the U, so this was about the covariance. Now when I'm transforming the vector, so I'm transforming U X, so X is K cross 1 now. It is just a vector with k number of rows and 1 column, and U transpose will be d cross k because I have just taken d eigenvectors. Now I have only d eigenvectors. So because it is transpose, so I just have d columns, but when I take transpose, I have d rows. With this, I get a small y. So I get a d cross 1y, a smaller y. So visually you can see that when I have transposed this x into this y, and then when I am projecting over here, for a x over here, say this is having a value, say 1 comma 5, so this x has value 1 comma 5, but when I transform this, I get some point, say over here, which has just one value, 2 suppose. So you can see the dimension is reduced. This 1 comma 5 became 2 over here. So it is the same thing. Here x was k cross 1. So in this case it was 2 cross 1. But now here it became 1 cross 1. So that depends on what value of d you take. So now we want to reconstruct. We want to come from here to here. Because after all, this is the space that matters. I cannot work in this space. Remember, this was our size and luminance. So I don't know what is E1 or E2. I know what is the size or the luminance. So we have to finally come into this space, right? So we'll also have to reconstruct the equation back. So reconstructing is basically u k cross d, that is you are basically just pre-multiplying with u on both the sides, and you see, because u is orthogonal, we know that u is orthogonal from the properties of covariance matrix. Here eigenvectors are orthogonal, so both of this will become I, and what you left with is k, so x. So x of k cross 1 will be nothing but u into y. So this is the reconstruction equation. So from here, using this reconstruction equation, you can go to here. And that was all. So this is the principal component analysis. So we saw that how can this data be compressed effectively so its variance does not hinder. And now one can ask a question, how to choose D. So how can I, so for this case, because there are only two, so that is okay. But if there are n dimensional data, so how can we choose what number of eigenvectors we should keep and which we should throw? So for that, there is no such actual method to choose D, but one can choose it using the energy method. So the energy method says that you calculate the energy of all the d eigenvectors by just adding all the variances. So see, if suppose I do this, so this is lambda 1, that is the variance in x1, and this is lambda 2, that is variance in x2. Sorry, lambda 1 variance in E1, and lambda 2, I have not written, so it is lambda 2 which is variance in E2. So if suppose I do lambda 1 square plus lambda 2 square, this particular thing will be like, say, take numbers. So suppose this is, say, 9, this particular thing is 9, and this particular thing is suppose some 1, suppose. So this thing is 1. So what I'm assuming is lambda 2 is 1 and lambda 1 is equal to 9. So you see, if suppose I square it, 9 squared plus 1 squared, so I get 81 plus 1, that is 82. So this is when I am taking all. So when I am taking all the k, so remember k were all the dimensions that I have. So I'll get this something 82. And if suppose I choose just one, I am just choosing this 9 thing, I am not choosing this. So I am just choosing the first one. So I get just lambda 1 square, which is 81. So you can see that this is still very close to this. So even after I have removed E2, the energy is quite similar. So we can find out a threshold which can be some 0.99 or 0.95. Using this I can find out the value of D. So choose a threshold such that the energy, the ratio of the energy, so ED upon EK, so ED over here is 81 upon 82, is less than is greater than some threshold which is 0.99 or 0.95, any threshold you can take that. Typically it is seen that D is 30% of K. So typically this is the value of D that we can take to get an effective compression. So that was all for the principal component analysis. I hope that you have understood this. Thank you so much for watching. Thank you.